Hi, my name is Luke Bieneman.
And my name is Tori Vidmar, and here is our presentation on antimatter propulsion.
Us humans dream of reaching beyond our solar system, but with today's technology, space travel on the order of light years is nearly impossible. Alpha Centauri, the star nearest to our sun, would take over 50,000 years to reach with our current technology. But there's future technologies thought to be only science fiction. Today we'll talk about one of these technologies known as antimatter propulsion. These engines are projected to be able to travel distances of up to 10 light years in only 200 years.
Okay, so a brief overview of antimatter. So matter-antimatter annihilation is currently the highest energy density propulsion concept. It has potential to transform space exploration by enabling faster interplanetary travel and deep space missions beyond our current capabilities. Current primary challenges include production, energy conversion, and storage and handling. A little bit of history. So in 1928, Dirac's equation predicts the existence of positrons. Shortly after, in 1932, Anderson confirms positrons through cloud chamber experiments. In 1955, antiprotons were discovered using high-energy accelerators, and now antimatter is routinely created and stored at large facilities like CERN. So now we will show you guys a short clip by Minute Physics explaining what antimatter is.
Pretty much everything in the universe is made out of matter. The Earth, air, you and me, stars, interstellar dust, all matter. By which we mean that these things are made out of electrons and quarks, and very occasionally other rarer matter particles like muons, tauons, and neutrinos. All of these particles are, at their fundamental level, excitations in everywhere permeating quantum fields. But as the famous quote goes, for every particle, there is an equal and opposite antiparticle, an opposite excitation in the everywhere permeating quantum field that has all of the exact same properties as that particle, except opposite charge. And since these antiparticles are opposite excitations of the quantum field, when a particle and antiparticle meet, they annihilate and destroy each other, which is pretty much exactly like how the equation x squared equals 4 has two solutions, 2 and minus 2, with the same value but opposite sign, and when they meet, they annihilate. Every fundamental particle has an antiparticle. There are anti-quarks, anti-neutrinos, anti-muons, anti-tauons, and of course anti-electrons, though we call them positrons.
So firstly we'll do a brief overview of antiproton-proton annihilation. So initially there is a proton and an antiproton, and the proton is just your normal proton. It's a baryon composed of 3 quarks, and an antiproton is just the opposite of that. It's made of antimatter, so it's made of 3 antiquarks. So to get the energy out of them, all you do is collide them. This collision releases gamma rays, and the total energy corresponds to equals mc squared, which is approximately 1800 mega electron volts. So this annihilation results in pions, gamma rays, and other particles that we'll go over later.
So now to compare this propulsion method with other energy generation methods, first we have chemical combustion, which results in a few megajoules per kilogram of energy. Solid is about 5 and liquid is around 1. For nuclear fission, it's 8 to the 10 to the 7th megajoules per kilogram, and nuclear fusion is 3.5 to 10 to the 8th. For antimatter, it is significantly higher than the other energy generation methods at 9 to the 10 to the 10 megajoules per kilogram, which is about 10 billion times more than chemical combustion, and 1,000 times more than nuclear fission, and 300 times more than nuclear fusion. Obviously, this looks very promising, but the real question is, can we efficiently use all of this energy?
Alright, so let's go into the science of an antimatter annihilation reaction. So I call it a reaction because it's kind of like a chemical reaction. So if you take a proton and an antiproton and you combine them, you are going to get pions of different charges. So you get 1.5 positive pions, 1.5 negative pions, and about 2 neutral charged pions. So then these pions almost immediately decay into gamma rays. This is energy loss. The neutral pions. The positive and negative charged pions decay into muons of their respective charges, which again is energy loss, and also neutrinos. And then the muons again decompose into electrons and more neutrinos. So all of that represents energy loss from the system, and if you can't efficiently use the muons or the pions or even the electrons, all of this results in energy loss from the system. So if you can't efficiently use the muons or the electrons created, you lose out on energy, and we won't be able to create as much thrust or have as high of an ISP. So what even are these things? What are muons, what are pions, all of that? So these are subatomic particles. You probably know what they are from physics. They're usually very high energy, at least some of the ones we're talking about, and they only exist for brief moments, at least the unstable ones. So these particles generally move at speeds close to light or at the speed of light. Pions are mesons, and they're particles composed of quark subparticles, and they only exist for, very, very, very small amounts of time, like 10 to the minus 8 seconds. Muons are positively charged leptons. These are particles, leptons are particles that are not composed of any other particles. They're like the base particles. And neutrinos are extremely abundant, and they're generally created in almost any reaction. So whenever 2 atoms hit each other, normally it produces neutrinos. A bunch of other reactions also produce neutrinos. And lastly, gamma rays are just a form of radiation. So they're photons. They're kind of similar to X-rays. Just as a summary, antimatter annihilation, it sounds like the most efficient form of energy generation, which it is, but it's not exactly E equals mc squared. In reality, the annihilation generates high energy particles like muons and pions, and these decay very quickly, which results in energy loss. So some of the challenges is we have a very, very small window, as you can see, on the order of 10 to the negative 8 seconds or 10 to the negative 6 seconds before some of these particles decay and we lose energy, to actually get that energy into the flow and create some sort of thrust or force or whatever. It's very difficult to actually convert these high energy particles into useful energy because they exist for a very short amount of time, they generally move very fast, and there's a whole lot of other complications with subatomic particles.
Okay, so let's explode our cats. First we have Zoe. Menace over here weighs about 3 kilograms, made of matter, so entirely made of protons, costs about $5. Then we have Ruby over here, weighs 3 kilograms, but of antimatter, and is entirely made of antiprotons. Ruby, on the other hand, costs $20 quintillion, and the US GDP in 2023 was $27 trillion, so for reference, Ruby costs 741 million times the US GDP.
Alright, so let's say we combined our cats and they exploded. How much energy would this create? Well, before we lose anything, it would produce 5.42 e to the 17 joules, which for your information is about 30,000 times the total energy in the bomb dropped on Hiroshima, and that was 63 kilograms of highly enriched uranium. But remember, we would immediately lose about 2.4 e to the 17 joules of energy due to the neutral pions decaying, so we only have about 3 e to the 17 joules left. So within 7 e to the minus 8 seconds, almost 0 time, we would lose another 8 e to the 16 joules due to charged pion decay into neutrinos, so we only have about 2.2 e to the 17 joules left. Then, within 6.2 e to the negative 6 seconds, again, it's not very much time, we would lose another 1.7 e to the 17 joules due to muon decay into neutrinos, so a lot of energy lost to neutrinos. So by the end, we'd only have about 5 e to the 16 joules of energy, which is only 3,000 times the energy of the bomb dropped on Hiroshima.
So a few performance metrics of antimatter propulsion. So an antimatter annihilation provides the highest energy yield, as we just went over, surpassing all other propulsion systems. It has a specific impulse of 10 to the third up to 10 to the 6 seconds, which is significantly higher than any other propulsion type. It has a thrust-to-weight ratio of 10 to the minus 3 to 1, and its cost per gram is about 6.4 trillion per gram, so obviously very high. Also, looking at these tables, so we can see that it has a converted mass fraction of 1, so it is able to convert all of its mass into energy.
So for antimatter engines, it's purely conceptual at this point. There's been no demonstrated engines made, so there is no state-of-the-art technology, but there are a few conceptual designs, so we'll walk through 4. This is the solid core proton-antiproton engine. As you can see, there's a hydrogen annihilation chamber that goes through a tungsten heat absorber and exchanger. So within this engine, 90% of the energy is transferred to the tungsten block. This tungsten block then heats hydrogen around here up to about 3,000 Kelvin, which is accelerated through the nozzle and produces thrust. So the ISP is in the 900 seconds range, and it's relatively high thrust. This is kind of like a thermal engine. The typical mass flow is around 7 kilograms per second. One thing to note is that there are temperature limits.
So the second concept we have is the proton-antiproton beam core engine. So what happens here is antiprotons meet with neutral H atoms where they are annihilated in this annihilation region, and then they turn into charged pions, which are accelerated out of the nozzle using a magnetic field. This contains about 40% of the initial annihilation energy, and this whole design has a very high ISP, about 28 million seconds.
So our third concept engine is the proton-antiproton plasma core engine. So within this design, we have a pulsed antiproton beam, which meets with a pulsed neutral or high atomic mass atom, something like H2. These collide and annihilate, which ionizes the hydrogen or whatever high atomic mass particle is in there, and that accelerates out of the nozzle, and it's guided by magnetic field lines, high energy magnetic field lines. So this has a higher ISP than chemical engines. The ISP is somewhere in the thousands, and it produces moderate thrust. The annihilation energy transferred to the hydrogen is only about 1.2%, so there's a lot of energy loss due to ionization, due to collision, coupling, things of that nature. And the typical pulse is about 10 to the 8 joules.
Okay, so now on to our fourth and final concept. We have the proton-antiproton gas core engine. And what's going on here is hydrogen and antihydrogen are sent into this chamber here where they annihilate, and the remaining hydrogen is then heated by the energy created by the annihilation and sent out of this nozzle. And only about 35% of the energy is transferred to the hydrogen propellant. It has a specific impulse similar to chemical engines, which is about 500 seconds, and a high thrust. And then typical antiproton mass flow rates range in about 10 grams per second.
So let's compare antimatter propulsion to some other propulsion technologies. So here we got 2 plots. As you can see, the first one is going to have specific impulse versus the thrust-to-weight ratio in G's. You can see antimatter is pretty far to the top right, which is where you want it. So it's a very broad scope technology, but that's just because it's not really established yet. It's conceptual, so these are just estimates. But the goal is to have as far up and as far right as you can on this chart, and antimatter is at the top of that. So then our second chart has jet power versus specific impulse. These acronyms are just like specific propulsion technologies. Most of them are nuclear, but the antimatter propulsion technology is this MAR right here. And again, you want to be in the top right, and you can see that's where MAR is. So where does it stack up? Antimatter is doing pretty well for itself. So is antimatter even feasible for space travel? We'll get into some considerations later, a lot of the downsides later. But first, let's just look at how much delta V do you need to get to various places. So we can see planetary, omniplanetary. I'm not going to read this whole chart, but we have various delta V's in the left chart, and on the right chart we have a delta V versus the antimatter mass, so how much antimatter mass is needed. So for example, to reach planetary orbit with a delta V of 10 kilometers per second, you don't need that much antimatter mass. It looks like it's about 10 to minus 9 grams, which is, it's a lot of antimatter. It's not that much mass. But for larger missions or missions that require payloads, you can see we're starting to have a lot more antimatter mass needed, and that scales with cost. So on the right side of this graph, you can see the cost increases exponentially. So with a payload, you need 6.4 times 10 to the 18 dollars. That's a lot of money, or more. So is it feasible right now? No, it is way too expensive.
So now a little bit about antimatter production. So current facilities produce about 1 to 10 nanograms a year, which is obviously not optimized for antiproton production at a space level. But here we have Forward's antiproton factory design. Basically, it uses high efficiency linear accelerator.
Have you ever had a dream that you have?
Basically, it uses high efficiency linear accelerators for proton beams. It also has a multi-stage cooling and deceleration process, and it eventually combines antiprotons with positrons to create anti-hydrogen atoms. Obviously, this is still all theoretical, and it's just an optimization of the production methods that we've considered. Cost projections. So a dedicated facility would be about $3 to $10 billion, producing only several milligrams a year. The cost per gram of antimatter is $6.4 trillion, so it's obviously very costly. And Forward's optimistic estimate is $10 billion per gram, with a few production facilities that are currently able to produce small amounts of antimatter. We have CERN, the European Organization for Nuclear Research, located in Europe, obviously. It's the world leader in antimatter research. They created the antiproton decelerator, which slows antiprotons produced in high-energy collisions to make them suitable for experimentation and observing. They also created the ENAE, the extra-low-energy antiproton, a decelerator that further reduces the speed of antiprotons for precision experiments. They've conducted multiple experiments such as alpha, A-trap, and base, and so far they've produced about 10 nanograms of antimatter. Fermilab, based in the US, is a major producer of antiprotons for high-energy experiments. They're mainly known for using the Tevatron collider. They have focused on proton-antiproton collisions to study particles like quarks and gluons, and they have produced 15 nanograms of antimatter, but unfortunately they shut down. Lastly, we have DESI, the German electron synchrotron. They specialize in high-energy electron-positron physics. They have created the Petra collider, which was previously operational at DESI, and was instrumental in a lot of positron-related experiments. And they're at the lower end, only producing around 2 nanograms of antimatter, but A for effort, so.
So there's a lot of challenges with the production of antimatter in general. It requires a lot of infrastructure, you need a particle accelerator, somehow to collect it, storage rings, etc. We'll get into storage later. It requires a ton of power to create, about 45 gigawatts of power, which is equivalent to 15 nuclear power plants. It's extremely expensive to produce and store antimatter, so the storage is about $10 to the $10 per gram. And these facilities, even the engines, they would be extremely expensive to launch, assemble, operate. Repairs are very expensive. And the current facilities that are able to produce antimatter are not optimized for creating antimatter. They're not like antimatter facilities. They're just large-scale colliders. So in order to actually scale to space, you would need dedicated facilities to generate antimatter.
So now on to storing antimatter. So how do we store it? Antimatter particles must be held in specialized traps. These are called Penning-Malmberg traps, which prevent them from coming in contact with normal matter as they will annihilate. So it uses a combination of static and electric magnetic fields to trap the charged particles. Additionally, the high-performance antiproton trap, the HIPAT, developed by NASA, was designed to hold 1 e to the 12 antiprotons for up to 18 days. But we would need thousands of traps to hold just nanograms of antimatter. So what are the challenges of storing antimatter? We went a little bit over it in the last slide, but obviously storage limit. So traps have a maximum charge density, and exceeding it causes instability and particle escape. So obviously not optimizing this, we're just losing energy and money. Particle loss, electric and magnetic fields can heat particles, which obviously will lead to collisions and heat loss. Lastly, antimatter storage. Antiprotons and positrons must avoid normal matter to prevent annihilation, like I mentioned before. So this will require a ultra-high vacuum and precise fields, which makes long-term trapping highly challenging.
So to summarize the challenges we've presented so far, firstly, while antimatter initially seemed very energy efficient, there's a lot of sources of losses. Think of the particle decay, even like ionization of hydrogen atoms if you're going that route. Loses a lot of energy. You don't exactly get equals mc squared. Next, it's extremely expensive to produce, like ridiculous. $6.4 trillion per gram of antimatter. You compare this to other fuel sources, other propulsion sources, generally much cheaper. Antimatter is also extremely hard to produce. Less than 30 nanograms have been produced ever. And even to produce it, we need dedicated factories that would need to be developed and constructed if we're talking about space travel. For storage, we need specialized Henning-Malmberg traps to isolate the matter from the antimatter. First, this limits the storage capacity, both in terms of overall storage and how long we can store it. It's very complex. If they fail, it's likely catastrophic in space. That's not good. And overall, just increased cost. It's very hard to store this. Lastly, as of right now, these antimatter propulsion systems are purely conceptual. They're in the before even development stages. That's what TRL is, technology readiness level. So it's just conceptual. They've never been demonstrated before. So just some other considerations quickly. The rocket core design must be able to absorb the charged particles and gamma rays. So remember, these are very high energy particles, very high energy photons and light rays. The core sizing and material selection are critical to absorb the energy. We need radiation shielding to protect humans, electronics, even just the material structures from damage, or humans could die. We need thermal radiators to reject waste heat. This is likely going to be pretty massive. The payload also needs to be moved away from where we're annihilating these antiprotons and protons, or sufficiently protected, so again, gamma rays and heat damage. Support structures for the chamber or for storage are likely going to be massive. That increases cost again. Another important consideration is that low molecular mass propellants like hydrogen will provide the highest high speed. It's kind of obvious, but. And lastly, transporting the antimatter to the reaction chamber and just in general needs to be very safe and efficient. Again, catastrophic damages if stuff goes wrong.
So a little bit about the current research initiatives. So current status, despite over 60 years of theoretical work, no antimatter propulsion system has ever been constructed or tested. Even test scale prototypes remain out of reach just due to challenges regarding production and storage, like we went over previously. Even now, current worldwide antiproton production is only about 1 to 10 nanograms per year, which is nowhere near the amount we would need. Some notable research initiatives. So CERN's antimatter research facilities continue to work on antimatter production and containment as of today. Additionally, NASA's EagleWorks Advanced Propulsion Lab has conducted theoretical studies on antimatter catalyzed fusion propulsion, which is kind of a hybrid between antimatter propulsion and nuclear fusion propulsion. Various university research groups have also worked on types of antimatter storage solutions. So here we have an example of the portable antiproton trap, which was developed by Penn State researchers.
So what does the future look like for antimatter propulsion? So antimatter propulsion enables spacecraft to achieve nearly relativistic speeds for interstellar travel. This efficiency drastically reduces travel time to distant planets and stars. This would help facilitate deep space exploration and enable missions beyond the scope of current chemical and nuclear propulsion technologies. So one opportunity is that in Earth's Van Allen belt, there are very low density clouds of antimatter. So this could possibly be used to refuel spacecraft. So what is the potential impact on space exploration? Again, it makes the exploration of neighboring star systems feasible within a human lifespan, so within the scope of 100-ish years. The high efficiency also allows for larger payloads and larger infrastructure development in space. So how does this get implemented? Scaling antimatter production by increasing production rates and reducing costs would be the first step. Advancing storage systems like the magnetic traps for long-term antimatter storage, and to design efficient systems to capture and utilize the annihilation energy. And here are our references.
Thanks for watching our presentation on antimatter propulsion.
Are you ready to do this?
Ready as I'll ever be.